Okay. Today I will start the chapter 5, which is the reduction of multiple subsystem. Okay.
Okay.
Okay, reduction of multiple subsystem. As you know, actually in the control system we have multiple block. Okay. So if you have multiple block like this, say this is one block. This is another. Okay. Like this. Say this is 1, 2, up to the, many blocks are there. So instead of this, you can bring those into one block. You can reduce the multiple block into one system. That is called the reduction of multiple subsystem. Okay, to reduce the multiple blocks into one block. That is the main thing. Okay. So see, in the block diagram, there are some components. What are the components? Like these are the signals. These are the signals, and this is the system. Can you identify the things? These are the signals. This arrow, and
Yes,
this block is known as the system. These are the system signals. These are the system. And if we do use this thing, this kind of thing, that is called the summing junction. That is called the summing junction. See here, R1, R2, R3. CS is the summation of these three. R1 plus R2 minus R3. And here is the pickup point. RS, RS. So from one block, from the one signal, we've got the three. So these are the components of a block diagram. These are the components of a block diagram. Okay. So that is our chapter, the reduction of multiple subsystem into one. So these are the components of block diagram. The first one is the signal. Some arrows are there. Say RS is the input, CS is the output. And these are the signals. And here is the system. System here, RS input, CS output. And this is the system. And these three, R1, R2, R3. So CS is equal to summation of these three. R1 plus R2 minus R3, because R3 has the minus symbol. And pickup point, RS. Okay. So these are the components of a block diagram for a linear time invariant system.
Okay.
Okay.
Yes.
Now see the cascaded form. Cascade means 3 blocks, say 3, 4, 5, many blocks up to n. Many blocks are in the series connection. These are the series connection. That means a cascaded connection. If those are in the series connection, then how you can reduce this block into one? Just multiply the transfer function inside the block. Say here RS is the input of the G1 and X2 is the output of the G1. Now, do you remember the formula? Formula is G1 would be output Laplace transform X2 by input, that is the R. Okay. So X2 by R. So what would be the X2? So X2 would be G1 into R, right? G1 into R. So X2 would be G1 into R. So G1 into R, this thing. Again, for the G2, again G2, if you look at the G2, output is what? Output is X1, input is X2. Or if I consider the x1 would be G2 into x2, right? G2 into x1. So we know the x2, we know the x1, as well as the C. So here the G3 is what? G3 is equal to C by x1. C by x1, or the C is equal to G3 into x1. So what would be the final value? So G3 is there. Instead of x1, you can write the G2 x2, and instead of x2, you can write the G1 R1, G3, G2, G1 R. That is a C. So, so as a result, what we'd say, this is your transfer function. G3, G2, G1. See. G3, G2, G1. That means those will be multiplied. Multiplication of the single block. There. These are the multiplication of single blocks. Okay. So do you understand this one, guys? Anyone there? Yeah, yeah.
Yes, sir.
Yes, sir.
Yeah,
Yes,
yeah,
sir.
is there? Yeah, yeah. Are you there?
Yeah, yes, sir.
Okay, you understand?
Yes, sir. Okay.
Okay. Okay. Let me know. Would you come to the campus tomorrow or not?
What, sir?
For the campus, I'll be there in the campus. If you need anything, you can come for the
Okay,
lab
sir.
or whatever it is. Okay.
Okay, sir. Inshallah.
Afternoon, sir.
Okay.
Tomorrow afternoon.
Yeah, it's up
No.
to you.
Tomorrow after
Yes, sir.
Namaz, inshallah.
Okay, okay, no problem. If you think that we should go to the campus and discuss about the lab, then you can come. You are welcome. Okay, I'll be
Okay,
there,
sir.
inshallah. And I can show you the laboratory things in the lab. Okay.
Okay, sir.
قد
Okay, now this is the cascade form. Now let's look at the parallel form. What would happen if the blocks are in the parallel? See this. Block G1, G2, G3, 3 blocks are there. And R is the same input for all of 3. Here the parallel summing junction is there, and the summation is there, will be the output. So for the parallel, there should be the summation. So remember, for the cascade, final output would be the multiplication of individual blocks. And for the parallel thing, for the parallel subsystems, the final result, or that means the output, would be the summation. Those would be summation. Okay. G1, G2, G3, those will be summation here. So for the parallel, it will be summation, and for the series, it will be cascaded. And feedback form is also there. R is the input, C is the output. See the feedback, transducer, input transducer. Oh, see one thing. This is the feedback, right? Each one is to, these are the feedback. But we can reduce the feedback in a technique. We have a technique here. These are the feedback, right? These are the feedback. They use reduce H1, H2 into 1, and G2, G3, and G1 into 1. Right. This thing will come, add here. We'll come here. Then finally they got this one, and after that they got this one. For this one, for this kind of figure, you can reduce this like this. Now here the thing is 1 plus minus GS into HS. So the question will arise, how would you distinguish, how would you define minus or plus or whatever it is? Thing is, you have to look at here. Say it is minus plus, the symbols will be opposite. For the minus it would be plus, and for the plus it would be minus. The symbol will be changed. Since it is minus plus, it would be plus minus. So it would be plus minus. GS into HS. GS divided by 1 plus minus GS into HS. RS input, CS output. Okay. Now we'll look at the figure, example. Let me make it full screen. How to show in the full screen? I don't know. What is the shortcut here? Okay, now look at the problem, example 5.1. The question is, reduce the block diagram to a single transfer function. Reduce the block diagram to a single transfer function. Okay, in that case, what would happen? So what we can do, first of all, we need to reduce this one, these three summing junction into one. That is our first job. And G2 and G3 and G1 into one. So first thing is first, make one summing junction, H1, H2, H3, G2 and G3. Now multiply G2 and G3 and reduce H1, H2, H3. H1, if I take minus, so how you reduce this one? Minus H1 plus H2 minus H3. Now take the minus common. H1 minus H2 plus H3. Okay. So instead of these three, we'll add this one. H1 minus H2 plus H3. And here we'll take the minus symbol as common thing. Minus will be common here. So H1 minus H2 plus H3, these would be the one subsystem from these three. But those are parallel. As those things are parallel, so it would be summation. Okay, and those will be multiplication. Now, next thing, we'll move it to here. If we move it to hit here, that would be G2, G3, G2, G1. And in the underground, no, let's keep it as it is. Now what they did, just reduce this one. So instead of this 3, this G1 is there. Now what would be the equation for this? G3 into G2. G3 into G2 here 1. Since it is minus, so it would be plus. G3 G2 into this one. H1 minus H2 plus H3. That would be the transfer function of this one. Now multiply G1. So G1 would come here. Okay. So there is a way to draw it to reduce this one. So first of all, remove the summing junction, make it 1. Second part, convert the parallel subsystem into single subsystem. That is the H1, H2, and H3. And finally, reduce the upper part, G3 into G2. G2 into G3. In the lower part, H1, H2, H3. Now reduce it and make this one. So that would be the final one. Now another one, block diagram reduction by moving blocks. So how would you reduce the block diagram by moving the blocks? That is the burning question. So those things will be given here. Look at here. See, RS into XS. So it is in the right side. So from the right, we are moving to it left, right to the left. So if you want to do so, then equation will look like this. Nothing will be changed. But if you want to move from the right to the left, then in the feedback, it would be 1 over GS. From left to the right, in the feedback form, it will be 1 over GS. Remember this thing. Moving junction, you are moving moving the block diagram for summing junction. So you are moving a block and you want to get the output. Okay. So that is the block diagram algebra for summing junctions. Now see another thing from the pickup point from say here. So you want to move, it would be look like this. And if you move from the left to the right, it would be only same thing. So if you want to move from the right to the left, then it would be 1 over in the feedback. In the feedback, it would be 1 over. Okay. This is the from the pickup point. Now we have another example. We need to look at this. Now see, the question is reduce the block diagram, right? Or to reduce the system into a single block. So it is possible for all of you to reduce the system with a single block. Okay, so now look at the figure here first. What are given? First of all, see what you can do. We can reduce the block. So first thing, move this one. Move this one from the right to the left of the pickup point. It will be 1 over G2S. 1 over G2S. And instead of this, we use this formula. Okay. All things are same, remain same. All things are remain same. Okay, now the sum, it will be sum. It would be sum. For the, after the summation, it would be sum. Sum and multiply it. Sum here. And instead of this, we reduce this one. G2 by 1 plus H2. Or just move around. G1, G2. So this is G1, G2. H2 by G1. Feedback, in the feedback, it will be 1 over. Now reduce this one. Finally, reduce the block. See, not very difficult, but you need to remember the steps. Which steps are necessary or which steps are required for your project, for your problem. Okay.
Okay, sir.
Okay, so remember the thing, the blocks which you have to reduce. Okay. So that is the way you can solve this one. Finally just cascade, multiply. Okay, another term which is the signal flow graph. Here, before that, we have used what? Before that, we have used the block diagram. We had the signal, we had the systems. Right now, we look at another part, which is the signal flow graph. We'll look at the signal flow graph. Okay. It is what? It is actually alternative to block diagram. So some of you do not want to use the block diagram instead of block diagram, you can use the signal flow graph, SFG. So signal flow graph or SFG is more familiar in the computer science department or computer engineering because they have used those things very rapidly, very frequently. So those are things, especially the graph thing are very important for this course. So signal flow graph or SFG. So here we have used few things. It consists of the branches system, alternative to block diagram. It consists of branches, which is also the system, and the nodes, which is the signal. So instead of nodes, they have used the signal. Instead of signals, they have used a node, and some have the branches. Okay, so that's the easy thing, not the difficult one. We are replacing the regular one into the new one, comparatively new one. So alternative to block diagram, signal flow graph is actually alternative to block diagram, and it consists of the branches, systems, and the node signals. like this, like this. So instead of block, you are using the branch, and instead of signal, you are using the nodes.
Hello, sir. One time again. What use branch?
Okay, branch is actually block diagram. Let me show you one thing. Say that is your system, right? So now if you convert it in the signal flow graph, then it will be, these are the signals, right? So we'll use this thing, and that is the system branch. Okay. So that is the branch. And these are the signals. You understand?
Yes, sir. Yes, sir.
Okay. So we can proceed. Okay. Example 5. Look at the example 5 carefully. What they have said. They have said that convert these figures into the signal flow graph. Okay. So according to the question, you have to convert these things into the SFG or the signal flow graph. How to do this? First, look at RS, CS, X2, X1. So how to convert it? Let's look. See. So at first of all, you need to identify the nodes. How many nodes are there? How many nodes are there? That is 1, 2, 3, 4. So just put 4. These are the nodes and systems. Say this is R, 2, 1, C. So R and X2, 1, X2 and X2, 1. So that is G1, G2, G3. It is R, X2 or V2 or V1, CS, whatever it is. So you have to draw the node first, then the branch. You can easily calculate. So that is the final answer. So they have converted to the signal flow graph. Similar thing would happen. How many branches are there? How many nodes are there? R1, X1, X2, X3. Say R, C, from the R, it goes to the G1, R2, X1, R2, X1, X2, X2, X3. Look at this. That would be the conversion of the given problem. And convert the cascaded parallel and feedback forms of the block diagram shown in the figure below into signal flow graph. So it is also same, not the difficult one. So first of all, you need to find out the signals, how many signals are there, and put the node according to the requirement. Yeah, and that's just done. So if you look that there is nothing, then that would be 1. The value is 1. If there is nothing to consider, then the value would be 1. Okay, okay, we have another one and another example. And so see, convert the block diagram figure below to a semaphore graph. So first of all, yeah, I need to find out how many signals are there and put those signals as a branch. Sorry, as a node. As a node, signal node, and then join. Then finally you will get the system, the signal flow graph. Conversion of the signal flow graph is done. Okay. Or you can simplify it. So instead of these two, you can write the G1. Instead of these two, you can write the G1, and other things are as it is. So it is as it is. Okay, the last topic of today's class, which is the Mason's rule. Mason's rule. Okay, the Mason's rule. So the thing is how to reduce the signal flow graph. A technique to reduce the signal flow graph to a single transfer function. So here the technique is you have to reduce the signal flow graph into a single transfer function using the Mason's rule. Requires the application of one formula. So you need one formula to apply. And what is the formula? Formula is given here, which is the GS equal to CS by RS is equal to summation of TK delta K by delta. Okay. Okay, so that is the transfer function. So someone is talking. Okay. Okay, so that is the Mason's rule. So using the Mason's formula, we can reduce the signal flow graph into a single transfer function. So for reducing the signal flow graph into a single transfer function, we need the Mason's rule. We need the Mason's rule. So here the Mason's rule is CS over RS is equal to summation of K, TK delta K divided by delta. Where K is the number of forward path, TK is the kth forward path gain, delta is the 1 minus summation of loop gains plus summation of non-touching loop gains taken 2 at a time minus summation of non-touching loop gains taken 3 at a time. Delta K is equal to 1 minus loop gain which does not touch the forward path. Okay. Now loop gain. What is a loop gain? The product of branch gains found by traversing a path that starts at a node and ends at the same node. Loop. You start from a node and you end it, and you traverse a path and end it at the same node. That is the loop. That will create a loop. Loop gain, the gain of the loop. The product of branch gains found by traversing a path that starts at a node and ends at the same node, that is called the loop gain. So here the first loop is the G2 into H1, loop 1, G2 into H1, second loop, G4 into H2, third loop, G4, G5, H3. That is third loop. Fourth loop, G4, G6, G4, G6, and H3. So these are the loops, 4 loops are there. And non-touching loop, loops that do not have any nodes in common. So the loops that do not have any nodes in common is called the non-touching loop. And non-touching loop gain is what? The product of loop gains from non-touching loops taking 2, 3, 4 or more at a time. That is the non-touching loop gain. So the product of loop gains from non-touching loops taken 2, 3, 4 or more at a time is known the non-touching loop gain. Okay. So here the non-touching loop is what? G2H1 is the non-touching loop. Non-touching loop gain, the product of loop gains from non-touching loops taken 2, 3 or 10. So see, non-touching loop 1, G2H1 into G4H2, second one G2H1 into G4, G5H3, third one G2H1 into G4, G6H3. So those loops are not common. So 2, 3, taking 2 or taking 3 at a time. Okay, an example is given here. Find the transfer function Cs by Rs for the signal flow graph in figure below. So a signal flow graph is given and you have to find out the transfer function, which is the Cs by Rs. Okay, so first thing first, you have to find out the forward path. Forward path is G1, G2, G3, G4, and G5. This is the forward path. How many forward paths are there? Only one forward paths are there. And how many loops are there? I can see there are 4 loops. Okay, so see carefully, very carefully. This is the forward path. That is the forward path. Forward path. And these are the loop 1. That is the loop 1, loop 2, loop 3, loop 4. So 4 loops are there. All loops are touching. There is no non-touching loops are not there. Okay, now see, find the forward path gain. So first of all, we have find the forward path gain, which is the G1, G2, G3, G4, and G5. Okay, forward path gain. And the loop gains, what I have explained few minutes ago, which is the loop gains. These are the loop gains. 4 loops. And the non-touching loops like L1, L3, L2, L3. And L2 and L3. These are the non-touching loop. Non-touching loop taken 2 at a time. Non-touching loops taken 3 at a time. L1, L2, L3. Okay. So from the delta and delta K, we know that delta is equal to 1 minus non-touching loop gains plus non-touching loop gains taken 2 at a time minus non-touching loop gains taken 3 at a time. And delta K is the formed by 1 minus loop does not touch forward path. 1 minus loop does not touch forward, which is a G7H4. So G7H4, this one does not touch the forward path. So it would be look like this. Delta. And the transfer function is just put the value, then you will get the transfer function. Okay. So that was the chapter 5.